Just it's working. It says it's being recorded. Okay, sounds good.
All right, great. So welcome everyone to our 10th Paleoclimate Advances Webinar Series. My name's Clay Tabor, and I'll be hosting today's webinar along with Sophia Makarowicz, who will be handling Q&A. Before we get started, a few reminders. By joining today's webinar, you agree to our code of conduct, which includes offering constructive feedback, considering new ideas, showing appreciation, encouraging innovation, acknowledging teamwork, and sharing the air. Regarding the webinar format, the webinar is organized into two 20-minute talks. At the end of each talk, there'll be about 5 minutes for questions. After both talks, there'll be an additional 10 minutes for further discussion with both speakers. And I'll give a verbal reminder to the speakers when they have 2 minutes of their 20 minutes remaining. A few overall reminders, excuse me. Here's a link to the PAWS website and Google Group. Also, if you have any speaker nominations, please let us know by filling out the form at the link below. And of course, any other questions, comments, or suggestions are also welcome. These talks will also be recorded and uploaded to YouTube for further viewing. All right, so the theme of today's talk is paleotempestology, specifically tropical cyclones in the past. It's my pleasure to introduce our speakers. Our first speaker will be Dr. Alexey Fedorov. He's a professor in the Department of Earth and Planetary Sciences at Yale University. Dr. Fedorov is also a senior visiting scientist at Sorbonne University. He studies ocean, atmosphere, and climate dynamics in the context of anthropogenic climate change and past climate variations. He's authored over 130 articles on a range of topics from El Nino and ocean atmosphere interactions to tropical cyclones and ocean circulation. He employs a hierarchical approach that incorporates both state-of-the-art global climate models and models of reduced complexity. Among his awards, Dr. Fedorov is a Guggenheim Fellow and a recipient of the Presidential Climate Change Research Award. Our second speaker is Dr. Lizzie Wallace. She's an assistant professor in the Department of Earth and Ocean Sciences at Old Dominion University. Dr. Wallace specializes in coastal geomorphology and climate science. Her research interests include developing long-term records of coastal climate extremes, such as tropical cyclones and nor'easters, using sediment cores and global climate models. She also explores the link between climate change and coastal processes and ecosystems. So with that, I'll stop sharing my screen. Dr. Fedorov, you can share your screen and begin your presentation. Thanks.
All right. Hello, everyone. I'm happy to be here and present this work on tropical cyclones and cyclogenesis. I have been working on this problem on and off for over a decade now. And these are sort of key papers published in my group. And most of the talk today will cover the first and the second paper. And I would like to acknowledge my collaborators here. First of all, several of my former postdocs, George Stadholm, Chris Briley, Les Muir, and then Kerry Manuel, Kevin Hodges, Sergei Gulev, and William Booth. All right, so we're obviously interested in tropical cyclones, not just in the context of paleoclimate. We're interested in anthropogenic global warming, how it would affect tropical cyclones. And in sort of a very crude way, we're thinking about the frequency of occurrence. And this is probably the most ambiguous thing. There are different ideas whether it will increase or decrease with global warming. Then we're talking about average strength. The consensus is that it will go up. It's basically the Clausius-Clapeyron. And finally, there is an important characteristic of tropical cyclone. It's their latitudinal range. And in particular, one of the concerns is that you may expect forward expansion of tropical cyclogenesis and in general tropical cyclone activity in warming climate. And this third topic will be the focus of today's talk. And in particular, there are two possibilities to consider. It's just, you can think about forward extension of TC tracks with warmer sea surface temperatures. Tropical cyclones can survive for longer, so the tracks can go much farther forward. And then there is another important factor, its potential forward expansion of a range of tropical cyclogenesis. And as I'm going to show, that most likely both factors are important in warming climates, whether we're talking about anthropogenic global warming or past climates, past warm climates. So just to give you some motivation for this talk, this is from recent years. First, Hurricane Henri in 2021. Not too strong hurricane, category 1. It's originated off Bermuda at about 33 degrees north, and then the landfall somewhat between Connecticut and Rhode Island as a tropical storm. You can imagine if it were a little bit warmer, it could have been easily category 2 or 3, and then it would have been really a disaster, a disastrous event. And another example, subtropical storm Alpha in 2020. It was the first recorded tropical storm that hit Portugal. And it's actually originated pretty far north, about 50 degrees north. It originated in the wake of an extratropical storm, and then it experienced tropical transition, and then landfall, you see a landfall over Portugal. It never reached a category 1 strength. Temperature of water of Portugal was about 22 degrees Celsius. But again, you can imagine a few more degrees Celsius above, and it would have been a real disaster. And so this is an important part. So this cyclogenesis, subtropical cyclogenesis that occur not in traditional sort of main development area of hurricanes, but farther forward, that's a part of the story. All right, so just a few more words about recent trends. Well, these are decadal trends in tropical cyclogenesis, tropical cyclone first recorded position, the tracks, and finally tracks density, the density of tracks. And especially I want to emphasize changes in track density in the North Atlantic. You can easily see higher density of tracks, and really the increase of this track density happens all the way towards New England and even farther towards Canada. And even if you look at the cyclogenesis, there is another interesting thing. So the red line here, so it's basically a blow up of the previous one of the previous panels. A red line here, it's 30 degree north latitude, and the red dots are first recorded position of tropical cyclones. And you can easily see that for the past 20 years, there are quite a few tropical cyclones that originated north of 30 degree north, and there is a significant increase of this number of cyclones after in the early 21st century compared to the 80s and the 90s. So this is quite an important factor It's hard to say how, whether it's nature of variability or it's a real trend, because again, we're dealing with 40 years of observations, but nevertheless, this is a very important factor. So to continue my talk, two important things. Well, trying to understand the distribution of tropical cyclones and potential changes, people use Genesis potential or Genesis potential index, and this is one of those indices shown here, and as well as potential intensity of hurricanes. So some of the theoretical considerations here, but for Genesis potential, it's largely empirical. And so some of the figures are based on this Genesis potential. So trying to understand changes in tropical cyclones in the past decades, we can look at SST trends. It's getting warmer. The North Atlantic is getting warmer. There is a clear trend in SST. Then calculating potential intensity of hurricanes and the trend, there is some indication of increase in potential intensity in the North Atlantic. And I'm just focusing on the North Atlantic for now. And if you use Genesis potential, there is some hints of stronger Genesis potential in the North Atlantic, but it's not overwhelming. And in particular, it's not overwhelming because GPI indices, they're not really designed for describing hurricanes at higher latitudes. And so it may be working in the main development area, but not that well north of 30 degrees north. Nevertheless, Genesis potential remains one of the ways to estimate what's going to happen with hurricanes, or potentially what happened with hurricanes in the past. And this is a compilation of several studies listed here, and we did it for this review paper. And we looked at all various simulations of large-scale simulations, model simulations of past climates, from the Holocene to the Pliocene to the Eocene and PETM. And we looked at simulated Genesis potential, what you can calculate from large-scale variables from a coupled model. And it gives you some idea what's happening with Genesis potential. And for most of the warm climates, there is a clear indication of a shift, poleward shift, both in the southern and northern hemisphere, especially in the northern hemisphere, poleward shift of cyclogenesis suggested by this GPI index. And we're talking about a few degrees to maybe 10 degrees shift in the maximum of Genesis potential, suggesting that in past climates, cyclogenesis indeed might have shifted poleward. This is compared to a potential shift for the between pre-industrial climate and today, just a few degrees. And again, this doesn't cover this change, what I just describe of more cyclones generated in sort of subtropics to mid-latitudes. All right, so this is suggestive of shift in the poleward shift of tropical activity in warmer climates. Well, we can do some simulations, and that's from this paper we wrote quite a while ago. And what we did, again, large-scale climate model in general, they're not very good in picking up tropical cyclones. They can pick up category 1, 2, strong cyclones, typically not their strength. And so you try to do some combination of different types of modeling. And this was for the Pliocene problem, and we focused on the reduction of meridional temperature gradient So the pink line, it's some reconstruction with expansion of the warm pool. And what you can do, you can run an atmospheric model and then run a downscaling model. And that was Kerry Emanuel's downscaling model. And this is for the present climate, and this is for the Pliocene. Colors indicate categories from tropical storms to category 5. And this downscaling model for this tropical expanded warm pool for the Pliocene suggests a real expansion of both cyclogenesis and tracks towards higher latitudes, as you can see here. Again, this is a very simple approach using SST reconstruction, then an atmospheric model, then a downscaling model. Another example comes from work of Jeff Keel with collaborators. They simulated hurricanes for PETM, the Paleocene-Eocene thermal maximum, a very warm climate, 5 to 8 degrees warmer than the Eocene, roughly 5 degrees warmer than the Eocene. And that's compared with modern tracks. What they did, they first ran a coupled model, then they ran an atmospheric model with high resolution. And that's the cyclone tracks. And again, undoubtedly, you can see the shift of tropical cyclone activity towards higher latitudes. A reduced cyclogenesis in the tropics, really. And most of the tracks are now extend much, much farther poleward. And this is just 2 examples of what you can do. And again, it suggests with warmer climates, you have an poleward expansion of tropical cyclones. One of the problems of this, either this approach, you're constrained by conventional large-scale GCMs, and then you really, even with a 1/4 degree of resolution, you have parameterized convection. So your tropical cyclone activity, your tropical cyclones are not necessarily strong, and even they're strong, it's parameterized convection. And so to really understand how tropical cyclones would change with significant warming in paleoclimates, you need to use cloud resolving or cloud system resolving simulations, which obviously problematic if you try to do it for a globe, if you try to do it for a realistic case, because you need to run them, such simulations, for a long time. What we did instead, we used cloud system resolving simulations using SAM, system for atmospheric modeling, with sort of idealized setup using an aquaplanet, a limited domain, so roughly 1/4 of a globe, fixed sea surface temperature forcing some idealized profiles of temperature. And it's non-hydrostatic model. Convection is explicit. Clouds are explicit. So we can use this to understand how tropical cyclones can evolve with climate change, especially with paleoclimates. And we use these 3 simulations with different meridional temperature gradient, equated to pole temperature gradient. And 3 simulations we have here, we call them modern analog, moderate mid-latitude warming, and exaggerated mid-latitude warming. So we increase temperature in mid to high latitudes and keep temperature the same in the tropics. So this is perpetual July, August. The ITZ shifted northward. And you can think it's a northern hemisphere somewhere. One thing to mention, so this is just an animation of these 3 simulations, how the model performs. You can see precipitation here by ITCZ, and every time you see a cross, this is a tropical cyclone of either in category, anything from tropical storm to category 5. Especially you can see many of those tropical cyclones in a very warm climate. You can think, so maybe the middle panel is like the Pliocene-like climate. The left panel is modern climate, and the very right, the Eocene-like, an Eocene-like climate. And just to show you, the model we use can reproduce very realistic hurricanes. This is category 4 with a nice structure, with strong precipitation, hurricane eye, everything what you expect from tropical cyclones. And so this is what we find from these simulations. So free distribution of tropical cyclone maximum intensity. So the purple, so we start with blue, it's modern climate, so it's the maximum intensity, it's about 12, 15 degrees north, and clearly with the warming, you get a shift of this distribution towards the subtropics. And finally, with the very warm climate, it's really a shift of distribution of maximum intensity towards the subtropics and mid-latitudes. And so this PETM simulations I showed before did get this nice expansion of tropical cyclogenesis towards the subtropics and mid-latitudes.
2 minutes left.
Thank you. And so why this happens? Well, we can look, and one of the major factor is changes in the jet stream. So this is the jet stream in these 3 simulations. So the jet stream becomes broader, its strength decreases, and there is a reduction of vertical shear in mid-latitudes that basically opens a new region for intense tropical cyclogenesis. You can look at potential intensity and vertical shear in these simulations in the Northern Hemisphere. And this is the shear. So the subtropics to mid-latitudes, you have a monotonic decrease in shear from the modern-like climate to moderate warming to very strong warming. A real significant decrease in shear that's favorable for tropical cyclogenesis. In addition, when we have very strong warming, you have an increase in potential intensity with yellow line, and that contributes to the Poleward expansion and actually the increase in the number of tropical cyclones. And finally, another important point, so these are tracks of tropical cyclones, but also tracks of extratropical cyclones. Extratropical, basically, it's strong synoptic storms that developed where you can track for a couple of days. And in modern climates, they're very much separated. Tracks of extratropical cyclones are very short, and there is virtually no connection. With the warming, you have a shift of tropical cyclogenesis and extension of tropical cyclone trajectories. And finally, in very warm climate, what you can see, there is this strong cyclogenesis in the subtropics to mid-latitudes. And what really happens, you can see these 2 end members. So these are tropical cyclones, these are extratropical cyclones. They have very different characteristics in the modern climate. But when you get to a very warm climate, and this is the last panel, so the 2 distributions, so this is extratropical, these are tropical climates. The 2 distributions, this is pressure and wind speed, they merge, and so you develop many hybrid cyclones. They start as extratropical with a typical mid-latitude synoptic structure, and then they develop into tropical storms. And so that's an important thing. So I'm at my summary. There is a tentative evidence that with global warming, recent global warming, There is an expansion of tropical cyclogenesis forward. It's relatively small for the time being, but modeling evidence suggests that for warm paleoclimate, there should be an expansion of this cyclogenesis to the subtropics and for sufficient warming to mid-latitudes. And you can expect many hybrid storms. They start with synoptic storms, but then they become tropical cyclones. And that concludes my talk. Well, thank you very much.
Thank you.
And just for fun, an animation of the same thing, but this is where you can particularly see the transition from extratropical cyclones to tropical in the left panel. All right.
Great. If anyone has any questions, feel free to raise your hand or put them in the chat. Oh, yes, Clay, go ahead.
Yeah, very interesting talk. I was curious if there's been work done on how well GPI does compared to simulations that can at least somewhat resolve tropical cyclones. So for example, you showed the GPI and the PETM simulation that is quarter degree, and then you mentioned that the GPI maybe isn't doing a great job in the mid latitudes. Has there been much comparison done to see how well it actually performs?
When we're talking, so GPI typically capture nicely the mean climate, right? The mean modern climate. And then qualitatively, they capture changes. For example, if you look, so this is this, maybe I can go back to this picture. So this is, the PETM experiment was outside of the range of this picture. So you have about 15-degree north shift in the northern hemisphere of GPI. And if you go to the actual simulation, qualitatively, it shows this shift, but it doesn't give you this dramatic shift towards higher latitudes. So it would give you some 15 degrees shift in the maximum GPI, but you have a broad range of cyclogenesis now. And so how well exactly it captures, I am not sure. So again, qualitatively, it captures the shift. Quantitatively, you need to look carefully, and we haven't done so. But again, a 15-degree shift, well, maybe it's good. Yeah. But the problem, so I think with past climates with a large signal, GPIs work relatively well. But when we try to use GPI trends for the past like 40 years to explain changes, observe changes, it's sort of marginally significant, and in some regions, it's not really working very well. Like in the Pacific, it's not working well at all for anthropogenic global warming over the past 40 years. But as long as you have a strong signal, then qualitatively they work nicely. With some limitation, obviously.
Great, thank you.
Go ahead, Betty.
So maybe a related question, and thank you for this talk. It was fascinating. I have lots of notes here, especially I'm interested in your cloud resolving model results. But for more related to what you were just discussing, in that plot, you showed the Oligocene had a fairly dramatic shift in the genesis potential in the Northern Hemisphere, but nothing in the Southern Hemisphere. Have you come up with an explanation for that?
Honestly, I'm very sorry. I haven't looked in details of this particular simulation. Yeah, I cannot answer this question, unfortunately. While yeah. So I sort of focused on Eocene and Pliocene and PATM. Oligocene is sort of not in my frame of reference yet, but it's obviously an important question.
I see there's a few more questions, but for the sake of time and make sure we can get through Lizzie's talk by the top of the hour, let's go ahead and switch over. Alexey, you can stop sharing, and Lizzie, you can share your slides, and then we'll have a bit of time if people are able to stick around at the end for additional questions.
Right. Okay, can you guys see my slides okay?
Yep.
All right, great. So hi, everyone. Today, I'm going to be talking about work that I've been doing that is sort of a large collaborative project spanning a bunch of different institutions, looking to understand how tropical cyclone frequency has changed over the Common Era. And so before I dive into this work, I just wanted to acknowledge all of my collaborators who are listed up here. And particularly, I wanted to give a big shout out to Wen-Cheng Yang and Gabe Becky at Princeton, who have been sort of co-leading this project with me. Okay, so why do we want to understand tropical cyclone frequency shifts in the past? Predominantly because they're pretty poorly understood today. And I think the last couple of hurricane seasons have really highlighted some of the sort of dramatic changes in frequency that can happen from season to season. So in 2020, we saw the most active hurricane season ever recorded in the Atlantic with 29 named storms, 12 of which went on to make landfall along the contiguous US coastline. But then just a couple of seasons later in 2022, we had half that number, so only 14 named storms in the North Atlantic, and only 3 of those went on to make landfall along the US coastline. And so this created sort of a lot of interest, I think, in the public and in the scientific community to sort of understand why we might see more or less storms in a given year. And as Alexey mentioned, tropical cyclone frequency is pretty poorly understood in the scientific community, so there's no accepted theory that explains the average number of tropical cyclones that occur each year on Earth. And models largely disagree about the sign of future tropical cyclone frequency change. So here we can see an example of this. We have what 2 different studies predict for annual TC number out to 2100. The blue line is showing a set of models that suggest storms are going to increase in frequency, and the red line shows a suite of models that suggest that tropical cyclone frequency will decrease. Really importantly, both sets of models match our observations shown in black really well. And so given that we have such a short set of observations, it's been really difficult to sort of validate either of these sort of tropical cyclone projections for the future. And so because of this, there's been a lot of interest in creating paleo hurricane records that can extend storm observations back thousands of years. And the way this has traditionally been done is by collecting sediment cores from back barrier ponds and lagoons. And so the way this proxy works is that during a storm event, you'll get high winds and waves, which pick up sand from the beach and essentially toss it back into these coastal ponds. In between these storm layers, fine mud from ambient conditions will accumulate in between. And so if I were to go and collect a sediment core in this basin, I could date these sand layers and then know when storm struck my location over thousands of years. And so this is precisely what researchers have been doing all up and down the Atlantic for the last couple of decades. So all of these black circles are showing you places where there are published paleo hurricane studies. Now, what do these records look like? So here on this next slide, I'm showing you an example of a published paleo hurricane record from South Andros Island in the Bahamas. To orient you, on the x-axis, we have time. So this is extending from about modern back to about 450 CE, so about 1,500 years. On the y-axis, we have a measure of coarse anomaly, which is an indication of how sandy our sediment layers are. So all of these black starred peaks are identified sandy layers in our core that we think correspond to a hurricane passage at this site. If we sum up the number of these events in a 100-year moving window, that's what you're seeing in this red line. And what we can see is that this proxy record indicates that there's been some dramatic shifts in hurricane activity in the past. In particular, we have what we call active intervals, so periods of time that span multiple decades where tons of storms are hitting a site, followed by periods of time where very few storms hit a site. And this is something that we see across all paleo hurricane records. So typically, a paleo hurricane record will show some sort of multi-decadal variability in the past. But it's really difficult to sort of interpret what climate has created this multi-decadal variability because paleo hurricane records are pretty biased. So they're only capturing sort of local hurricane strikes at high intensity. So this record that I just showed you from South Andros only captures storms that pass within 100 kilometers of the site at category 3 and above intensity. And so what this means is that it's really, really difficult to sort of infer large-scale hurricane climate from a single record. What I show you when I'm presenting a record from sort of South Andros Island is only how hurricane activity has changed at that site. And so this tends to be somewhat dominated by random variability and not by climate. And so in recent years, there's been a big push to create sort of compilations of paleo hurricane activity to better capture sort of a regional hurricane climate signal. So here you can see an example of one such compilation that pulled together records from 4 different sites in the Bahamas. And so what you might notice is that compilation has multi-decadal scale variability, but it's not really at the same sort of scale as the single record. And so given sort of all of this background and this interest in creating more compilations, myself and my collaborators decided it would be cool to create sort of an Atlantic basin wide compilation of sediment cores and compare that with some tropical cyclone model estimates of hurricane frequency over the past millennium. And in particular, we wanted to do this to sort of answer the following question, which is, do current tropical cyclone model frequency estimates match sediment estimates of what storms were doing in the past for sort of the past millennium? Okay, so to do this, the first step is we have to create this sediment reconstruction. So we take all of the existing records in the Atlantic and we sort them into 12 different regional composites, pretty much purely based on geographic location. So you can sort of see where the different regions are here in the map. And then on the left, you can see what these different regional compilations look like. So on the x-axis, we have time from 850 to 2005. And then on the y-axis, we just have the list of all of these regions. So all of these colored stars are showing you the median age of events or sediment layers that were coarse in these cores. And so it's basically an indication of when we think storms pass by these regions over the past millennium. But since this is a paleoclimate audience, I'm sure you guys all are aware that proxies are often associated with some level of age uncertainty. So to create our overall compilation, we have to take into account that each one of these events can't really be represented by like a single dot. And so to create our overall compilation, we follow sort of these 4 steps broadly. So each event is randomly perturbed within age uncertainties. Then we weight all of the records by the return period of storms to each site. So records from the Bahamas, typically, well, in general, the Bahamas has a lower return period, so it sees more storms than places like New England. And so we make sites that see more storms more important to the compilation overall. So after we've weighted our records, we sort of sum them all up And then we repeat this process 2,000 times to create some sort of estimate of age of uncertainty in our hurricane frequency compilation. So what does this estimate look like? Here you can see our sediment-based hurricane composite. And so the black line is the mean of the 2,000 estimates, and the gray bar is the standard error of those 2,000. And so what we see is that there has been, according to our sediment estimate, multi-decadal variability in storms in the past, with an increase in storms during sort of the 1400s as well as during the 1800s. Another thing that you might notice is that hurricane activity during the modern interval, so about the last 100 to 200 years, is not exceptional compared to the past millennium. So there's been a lot of interest in understanding whether hurricane frequency today is substantially different from what's been happening in the past. And according to at least our sediment estimate, it doesn't seem like the last century has been exceptional compared to the past millennium. Okay, so we have our sediment estimate, but how does this jive with sort of tropical cyclone model frequency estimates? So to get an estimate of Atlantic tropical cyclone frequency in the, using models, we use sort of a simple approximation. So we approximate model frequency, or sorry, hurricane frequency as a function of tropical relative SSTs. So we take temperatures over sort of the tropics in the Atlantic compared to tropics everywhere. And this has been a method that is often used in the Atlantic for sort of seasonal and decadal hurricane prediction really successfully. So we thought we would apply it to the past millennium. So then our next step is to get sort of past millennium estimates of sea surface temperatures. So we decided to use two different types of reconstructions. We used the CSM last millennium ensemble, which you should think of as sort of the more traditional global climate model. And then we also used a data assimilation reconstruction known as the last millennium reanalysis. So I'm going to briefly walk through how both of these are built so we can understand the differences. So starting out with CSM, typically global climate models start with some level of climate forcing, things like solar, volcanic, greenhouse gases. These provide initial and boundary conditions to a model. Then the model physics sort of takes its course and spits out some sort of estimate of annual SSTs that are based purely on model simulation. On the other hand, a data assimilation reconstruction like the LMR starts out pretty similarly. It has similar climate forcing, solar, volcanic, greenhouse gases, but the differences lie in the next step. So in the next step, data assimilation reconstructions are constantly assimilating proxies that have estimates of sea surface temperature and sort of forcing the model to represent what the proxies say sea surface temperature should have been at that time. And so ultimately you end up spitting out an estimate of annual SSTs that is informed by paleoclimate data. And so I want to argue that LMR is sort of as close as we can get to the real world, because unlike traditional GCMs, it's actually assimilating real internal climate variability that we can only find in proxies. Okay, so we have our two estimates of SSTs. What does a sort of hurricane frequency estimate using them look like? So we're going to start out with the LMR. So here we can see our LMR hurricane frequency estimate in blue and orange. These are two different generations of LMR compared to our sediment estimate in gray. And so what we find is that both of these estimates exhibit multi-decadal variability in storms for the past millennium. And it turns out they match each other surprisingly pretty well. So they are statistically significantly correlated at a value of 0.36. But how does the CSM last millennium ensemble match up? So here we can see our CSM estimate of hurricane frequency shown in red compared to our hurricane sediment estimate shown in black and gray. And so what we found is that CSM doesn't tend to produce this multi-decadal variability. It seems to be really sensitive to sort of external climate forcing. So we've got this sort of peak in the 1200s when we know there was sort of a large volcanic eruption. We've also got sort of declining frequency as we move towards the modern with increasing greenhouse gases. And none of this stuff shows up in our sediment estimates. And so this kind of brings us to the answer to that question that we've been asking, which is, I guess the other thing that I forgot to say is that we don't really find a strong relationship between these two, which was maybe obvious by looking at this, but there's no correlation between the sediment estimate and CSM, estimate of hurricane frequency. So this brings us to the answer to sort of our big overarching question, which is, do current tropical cyclone model frequency estimates match sediment estimates for the past millennium? And so the answer is sort of yes, a little bit no too, depending on what SSTs you're looking at. But it seems like we can produce a sediment estimate and a model estimate that show multi-decadal variability in hurricane frequency over the past millennium. In general, simulations that are sort of assimilating real internal climate variability, like the last millennium reanalysis, tend to match our sediment reconstruction better than more traditional GCMs like the CSM last millennium ensemble, which we think has sort of structural biases in sea surface temperatures and therefore does not. And sort of an additional conclusion that we can draw from this work is that perhaps natural climate variability, things that are included in the LMR that are not included in sort of traditional GCMs, play a more important role in creating multi-decadal shifts in hurricanes in the past than just simply external climate forcing. And so having done this work, you might, or having read this conclusion or heard me say it, you might be interested to learn a little bit more about what sort of natural climate variability in the LMR seems to be producing these active and quiet intervals of storms. So we also decided to take a look at that. So that's what you're going to be seeing on this next slide. So here we can see LMR relative tropical SSTs for the globe correlated with our hurricane sediment estimate. And all of the stipples are sort of significant correlations. And then on the right side of the screen, we're showing just the same thing, but a regression. And so what we noticed relating these two estimates is that hurricanes tend to be more frequent in the past millennium when there is warmer tropical Atlantic conditions, which sort of makes sense. And then also when we find sort of a negative interdecadal Pacific oscillation. So this was something that we could learn from this sort of data model comparison world. In terms of sort of where this work is headed, my lab is currently working to try to downscale tropical cyclones using a model out of Carrie Emanuel's group for the LMR. So we're taking sort of the sea surface temperatures from the LMR, coupling a high resolution atmospheric model onto them, and then giving all of that to sort of a downscaling model to create storm tracks for the past millennium. And we're doing this because we want to sort of answer two questions. So we want to know, how does large scale climate variability impact hurricane activity on decadal and longer timescales in a model world? And then we also want to understand sort of what is the capacity of this sort of suite of paleo hurricane records to better sort of inform our understanding of these climate controls on hurricane activity in a real world. So we have a huge suite of paleo hurricane records, but can we create useful basin scale compilations with them, and how many do we need to do that? So this is sort of work that I'm actively starting, and so I don't unfortunately have any cool results to show you guys today, but it's sort of a little teaser for what we're going to be doing next. The other sort of teaser that I wanted to throw at you guys is we're also, myself and folks at Hui and Texas A&M are working to create what we're going to call Paleo HURDAT, which is the first database of paleo hurricane records in the North Atlantic that's going to have sort of all the metadata and data that you might need for third-party usage. We feel like this is something that doesn't actually exist and makes it really difficult to create compilations like the one I showed today. So to give you sort of a teaser for what this looks like, we've already got the website sort of spun up, so you should be able to go click on a paleo hurricane record, plot up the sediment data, plot up when events happened, plot up your age model, and then of course, be able to go and just directly download that file. So we're hoping that this will sort of be coming out in the new year, because we've got it sort of prepped and ready to go. And so with that, I think I'm reaching the end of my time. So I would love to hear your questions or ideas or feedback. Thank you for listening.
Thank you so much. Great talk. If anyone has any questions for Lizzie, please, raise your hand or put your question in the chat. Yes, Ren.
Yeah, thanks, Elizabeth. This is very fascinating work. I was wondering, so how far do those records go? Because we have other simulations that go a lot further back. And the other question is, there looks like there's might be some kind of a periodicity potentially, or in your Atlantic hurricane record. Have you done things like spectral analysis to see if they correspond to some of the modes of variabilities, like Atlantic mode decay over oscillation or something like that? Yeah.
Yeah, great questions. I guess to the first one, these records rarely go back more than 6,000 years. And I would say like the wealth of records that we have that go back more than 2,000 years is pretty sparse. So it's like if I had that map of all the sites, if you got rid of the ones that go back more than 2,000 years, you would have like a substantially smaller pool. So we have a hard time creating records with sediment, at least, that go back far in time. I think there's hope to try to use different proxies like speleothems to reconstruct storms in the past and much deeper into time. But I don't know if anyone has been successful at that yet, because it's pretty complicated. And then your other question was whether we've done any sort of spectral analysis. So no, yeah, we've pretty much just created this record. There's a preprint out on it, but it's not yet published. But yeah, I think it would be cool to do some more detailed statistical analysis of both the compilation and the sort of hurricane frequency estimates.
Great, thank you.
Yeah.
Yes, Alexey?
Very nice work. It's actually amazing that you can actually get this correlations at all, because I remember your earlier presentation, like a few years ago, you did at Yale. You couldn't find any connection with climate variability. Now it's there. But nevertheless, my question is, your method is sort of biased towards landfall in hurricanes. Is there any hope to do some estimates of hurricanes in the open ocean? I don't know, some sedimental cores or something?
I don't know how I would do that. The best you could do would try to get sort of estimates from like Bermuda, but even there is still not the open ocean. The problem with like deep sea sediment cores is they're going to be really coarsely resolved. So you would maybe go further back in time, but you wouldn't be able to say like with high frequency, like when a storm hit in a given year. And yeah, I doubt storms are really impacting the deep ocean either. But yeah, so I don't know. We are kind of biased to landfalling storms, and we're making an assumption that landfalling storms sort of reflect overall frequency variations, which I think is a decent assumption based off at least the historical data. But yeah, it would be great to expand the network more. But yeah, I think we will be limited to sort of island records. So maybe like the Lesser Antilles would really help. getting a few more storms.
Thank you. Thank you.
Yes, Betty?
Yeah, thank you. This was great to listen to. I guess I had two questions. One was why annual SSTs? When you think of tropical cyclones, I normally wouldn't think of annual SSTs. And the other was the LMR. I haven't kept up with it completely, but is that still the offline data assimilation? And have you looked at then the Perkins and Haycom online data assimilation and see how well it does or how different it is?
We haven't looked at the latest online version yet. But yeah, I think that would be cool to do. But I think at some point we just had to make a cutoff and be like, oh, we're going to try to publish this. And I'm not sure it was out yet at the time. And then your other question, I think I've forgotten it now. There was another part, but I'm not sure what it was.
Betty, I think she was asking about the why you're using annual sea surface temperatures.
Oh, yes. So the LMR only spits out annual SSTs. So to be sort of, we could have used monthly for CSM, but we decided to just use annual to be sort of an apples to apples comparison. And the hurricane records are nowhere near, annual resolution in most cases. So there was a lot of smoothing involved as well to get down from, like, you went from annual to multi-decadal smoothing to sort of match up with the sediment records.
I see a question in the chat from Bronwyn. She says, can you talk a bit more about how we can be confident that the coarser grain layers in these various sediment cores correspond to tropical cyclone frequency rather than tropical cyclone intensity? And great talk.
Yeah, so I guess we think they correspond to frequency. They are related. It's all kind of related. So we're really only capturing intense storms. But the thing we do with these records is usually there's a few modern deposits. And we look to see what storms have passed over the site in the modern. And then we make some sort of guess as to which events were captured based off of usually intensity. So the initial record that I showed you from sort of South Andros Island had 2 events that were found in the modern, but that was only a small subset of the storms that have gone over. And so there had only been sort of 2 intense storms that had gone over the site recently. So we just kind of made the assumption that our record was only capturing those 2 intense storms. And that's typically what we do with every paleo hurricane record. There's some level of calibrating sort of the modern to modern storms and figuring out which ones we think left deposits, which are usually related to the intensity of the storm. But I don't know how we would go about reconstructing the intensity of the storm. It's mostly just whether or not an intense storm happened to leave the deposit.
All right, we're at the hour. I know there's still some more questions, so but we can open it up to general questions for either speaker, and happy to stick around for a bit longer if people want to continue the discussion.
If you were able to stay on, Jack, feel free to ask your question.
Sure, great, thanks. Yeah, so this sort of follow-up for what Elizabeth was just talking about. So when you basically have this record of Atlantic, tropical cyclone frequency, how well does that compare to, say, like the 20th century?
Yeah, so it compares decently well to the 20th century. So we were able to kind of show first that it matched 20th century estimates, at least the basin-wide comparison. And then that kind of, again, gives us faith that it's doing a decent job in the past.
And I just had one other, which is, so you had your sediment record matches the LMR reconstruction like quite nicely, seems like. And so was sea surface temperature really like the main driving variable, or were you able to look at the LMR and sort of pull out if, something else was impactful?
Yeah, so we were only feeding in just these tropical relative SSTs. It's all that we took from the LMR, and we didn't play with anything else. Our current work is trying to now simulate tropical cyclones using LMR SSTs, but again, we're planning on running a different atmospheric model coupled with that. But we haven't played with anything else in the LMR yet, but I do think it would be cool.
Yes, Ren?
Yeah, I actually had a question for Alexey. So Alexey, in your 2010 paper, it was really fascinating that the polar expansion of tropical cyclones also help maintain the shallowed the equator to mid-latitude temperature gradient through the enhanced ocean mixing. So I was wondering, since then, have your group looked at the effect of this polar expansion of tropical cyclones on the ocean mixing in the coupled framework? And do you know any work have tested that? I think you're muted.
You are muted.
Sorry. Yeah, we wrote a paper with my former student, Georgy Manchurian, I think it's 2013, where we used a coupled model of CSM1, and we introduce intermittent mixing in sort of subtropics, in the region where you expect, subtropics to mid-latitude, the region where you expect like an increase in tropical cyclones. And it was idealized sort of on and off increase in vertical diffusivity. Mm-hmm. Not real tropical cyclones, but just an increase. And we looked at climate effects of this on longer time scale, like if you run a model for 50 years or so. And so what we found, one of the effects of this mixing is remote effect on the cold ton in the equatorial Pacific. So there was about 0.5 to 1 degree warming of equatorial cold ton. And then with enhanced ocean heat uptake, we also get some warming in higher latitudes. So yeah, the impacts were not huge, but they were there. So you can take a look at that paper, I think 2013 or 2014, Manchurian, Fedorov, Bryle and Fedorov.
Okay.
Yeah.
Okay, cool.
But again, it's idealized. It's not real hurricanes, just changing vertical diffusivity intermittently.
Right. So I was just wondering, so has anybody tested that in the actual coupled framework?
So that was a coupled model. That was a coupled model.
Right, just from like a high resolution.
But high resolution, I know that my former postdoc, Hu-Wei Li, who is now at NCAR, is testing this. Yeah, I haven't seen her latest work, but she's basically looking at high-res models and how hurricane mixing affects climate and ocean circulation.
Okay.
Yeah.
Cool. Thank you.
If no one else has any questions, then I'll call it there. Thank you so much again to our speakers, Lizzie and Alexey. Thank you so much for your time. Let me stop the recording.